Hello friends, in the last discussion we talked about relativity of length, the Lorentz transformations and Doppler effect for light. In today's lecture we shall be talking about relativistic quantities. Relativistic linear momentum. Suppose that a number of observers, each in a different inertial reference frame, watch an isolated collision between two particles. In classical mechanics, we have seen that even though the observers measure different velocities for the colliding particles, they all find that the law of conservation of momentum holds. That is, they find that the total momentum of the system of particles after the collision is the same as it was before the collision. How is this situation affected by relativity? We find that if we continue to define the momentum p of a particle as mv, that is the product of its mass and its velocity, then the total momentum is not conserved for the observers in different inertial frames. We have two choices: give up the law of conservation of momentum or see whether we can refine our definition of momentum in some new way so that the law of conservation of momentum still holds. The correct choice is the second one. Consider a particle moving with constant speed v in the positive direction of an x-axis. Classically, its momentum has magnitude p is equal to mv and is equal to m delta x upon delta t. Here, delta x is the distance it travels in time delta t. To find a relativistic expression for momentum, we start with a new definition: p is equal to m delta x upon delta t 0. Here, as before, delta x is the distance travelled by a moving particle as viewed by an observer watching that particle. However, delta t 0 is the time required to travel that distance, measured not by the observer watching the moving particle, but by an observer moving with the particle. The particle is at rest with respect to this second observer. Thus, the measured time is a proper time. Using the time dilation formula, delta t is equal to gamma t 0. We can then write p is equal to m delta x into delta t divided by delta t into delta t 0 and is equal to m into delta x upon delta t into gamma. However, since delta x upon delta t is just the particle velocity v, we have p is equal to gamma mv. Note that this differs from the classical definition only by the Lorentz factor gamma. However, that difference is important. Unlike classical momentum, relativistic momentum approaches an infinite value as v approaches c. We can generalize this definition to vector form as p is equal to gamma mv. This equation gives the correct definition of momentum for all physically possible speeds. For a speed much less than c, it reduces to the classical definition of momentum p is equal to mv. Relativistic energy. The science of chemistry was initially developed with the assumption that in chemical reactions, energy and mass are conserved separately. In 1905, Einstein showed that as a consequence of his theory of special relativity, mass can be considered to be another form of energy. Thus, the law of conservation of energy is really the law of conservation of mass energy. In a chemical reaction, the amount of mass that is transferred into other forms of energy or vice versa is such a tiny fraction of the total mass involved that there is no hope of measuring the mass change with even the best laboratory balances. Mass and energy truly seem to be separately conserved. However, in a nuclear reaction in which nuclei or fundamental particles interact, the energy released is often about 1,000,000 times greater than in a chemical reaction, and the change in mass can easily be measured. An object's mass m and the equivalent energy E0 are related by E0 is equal to mc square, which without the subscript 0 is the best known science equation of all time. This energy that is associated with the mass of an object is called mass energy or rest energy. The second name suggests that E0 is an energy that the object has even when it is at rest, simply because it has mass. Table here shows the approximate mass energy or rest energy of a few objects. In practice, SI units are rarely used with mass energy equation because they are too large to be convenient. Masses are usually measured in atomic mass units, where 1 U is equal to 1.66 into 10 raised power minus 27 kg, and energies are usually measured in electron volts or multiples of it, where 1 electron volt is equal to 1.60 into 10 raised power minus 19 joules. Total energy. The mass energy equation gives for an object the mass energy 0 that is associated with the object's mass m, regardless of whether the object is at rest or moving. If the object is moving, it has additional energy in the form of kinetic energy k. If we assume that the object's potential energy is 0, then its total energy E is the sum of its mass energy and its kinetic energy, as E is equal to E0 plus k and is equal to mc square plus k. Although we shall not prove it here, the total energy E can also be written as E is equal to gamma mc square. Here gamma is a Lorentz factor for the object's motion. In our earlier lectures, we discussed a number of examples involving changes in the total energy of a particle or a system of particles. However, we did not include mass energy in the discussion because the changes in mass energy were either 0 or small enough to be neglected. The law of conservation of total energy still applies when changes in mass energy are significant. Thus, regardless of what happens to the mass energy, this statement is still true, that is, the total energy E of an isolated system cannot change. For example, if the total mass energy of two interacting particles in an isolated system decreases, some other type of energy in the system must increase because the total energy cannot change. In a system undergoing a chemical or nuclear reaction, a change in the total mass energy of the system due to the reaction is often given as the Q value. The Q value for a reaction is obtained from the relation system's initial total mass energy is equal to system's final total mass energy plus Q, or E0I is equal to E0F plus Q. Using equation E0, is equal to mc square, we can rewrite this in terms of the initial total mass mi and the final total mass mf as mi c square is equal to mf c square plus q, or q is equal to mi c square minus mf c square and is equal to minus delta mc square. Here the change in mass due to the reaction is delta m and is equal to mf minus mi. If a reaction results in the transfer of energy from mass energy to, say, kinetic energy of the reaction products, the system's total mass energy E0 and the total mass m decreases and Q is positive. If instead a reaction requires that energy be transferred to mass energy, the system's total mass energy E0 and its total mass m increases and Q is negative. For example, suppose two hydrogen nuclei undergo a fusion reaction in which they join together to form a single nucleus and release two particles in the process. The total mass energy and total mass of the resultant single nucleus and two released particles is less than the total mass energy and total mass of the initial hydrogen nuclei. Thus, the Q of the fusion reaction is positive and energy is said to be released, transferred from mass energy by the reaction. This release is important to you because the fusion of hydrogen nuclei in the sun is one part of the process that results in sunshine on earth and makes life here possible. Kinetic energy. In our earlier lectures, we defined the kinetic energy K of an object of mass m moving at a speed v well below c to be K is equal to half mv square. However, this classical equation is only an approximation that is good enough when the speed is well below the speed of light. Let us now find an expression for kinetic energy that is correct for all physical possible speeds, including speeds close to c. Using total energy equation for K leads to K is equal to E minus mc square and is equal to mc square into gamma minus 1. Here gamma is the Lorentz factor for the object's motion and its value equals 1 upon under root 1 minus v upon c whole square. This figure here shows plots of the kinetic energy of an electron as calculated with the correct definition and the classical approximation, both as functions of v upon c. Note that on the left side of the graph, the two plots coincide, that is, the part of the graph where we have calculated kinetic energies so far. This part of the graph tells us that we have been justified in calculating kinetic energy with the classical expression. However, on the right side of the graph, at speeds near c, the two plots differ significantly. As v upon c approaches 1, the plot for the classical definition of kinetic energy increases only moderately, while the plot for the correct definition of kinetic energy increases dramatically, approaching an infinite value as v upon c approaches 1. Thus, when an object's speed v is near c, we must use this equation, that is, k is equal to mc square into gamma minus 1 to calculate its kinetic energy. This figure also tells us something about the work we must do on an object to increase its speed by say 1%. The required work W is equal to the resulting change delta K in the object's kinetic energy. If the change is to occur on the low speed, that is on the left side of the figure, the required work might be modest. However, if the change is to occur on the high speed, that is right side of the figure, the required work could be enormous because the kinetic energy K increases so rapidly there with an increase in speed V. To increase an object's speed to c would require, in principle, an infinite amount of energy, thus doing so is impossible. The kinetic energies of electrons, protons and other particles are often stated with the unit electron volt or one of its multiples used as an adjective. Momentum and kinetic energy. In classical mechanics, the momentum p of a particle is mv and its kinetic energy k is equal to half mv square. If we eliminate v between these two expressions, we find a direct relation between momentum and kinetic energy as p square is equal to 2 km. We can find a similar connection in relativity by eliminating v between the relativistic definition of momentum and the relativistic definition of kinetic energy. Doing so leads, after some algebra, to Pc square is equal to k square plus 2 kmc square. Using the total energy equation, we can transform this equation into a relation between the momentum p and the total energy E of a particle as E square is equal to Pc square plus mc square whole squared. This right triangle can help you keep these useful relations in mind. You can also show that in this triangle sin theta is equal to beta and cos theta is equal to 1 upon gamma. The momentum and the total energy relationship equation shows that the product Pc must have the same unit as energy E. Thus, we can express the unit of momentum P as an energy unit divided by c in fundamental particle physics. So friends, here we come to the end of our discussion in this lecture and therefore we sum up. The definitions of linear momentum, kinetic energy K and total energy E for a particle of mass m are valid at any physically possible speeds. Gamma is the Lorentz factor for the particle's motion and mc square is the mass energy or rest energy associated with the mass of the particle. When a system of particles undergoes a chemical or nuclear reaction, the Q of the reaction is the negative of the change in the system's total mass energy. So that is it about relativity. Hope you must have enjoyed the learning process. Thank you very much.